Hey there, Mr. Sutton here, bringing you the Pre-Cal Honors 7-3 Extra Practice Number 2 Solutions on Parametric Equations. This one we've got a puzzle to solve, so let's go ahead and see what that is. So here's the puzzle. This is an answer checking anagrams puzzle. The idea is you have to solve all these problems. In this case, write each pair of equations in rectangular form and then say what conic section shape it is. And I've also actually given you the answers. If you go to the very end, here are some answers, question mark. The catch is some of these are wrong. When you find a wrong answer, you have to circle it or write it down and then unscramble those letters that you've circled or written down to spell something relevant to this chapter. So with that in mind, let us proceed. For problem A, we've got this pair of parametric equations. My strategy on all these is going to be pretty similar, at least when I have trig functions involved. I'm going to try to get the trig functions isolated and then square them, and then use one of my Pythagorean identities to rewrite things in terms of x and y. So same strategy every time. So let me start with this x equation here. Let me first start by dividing both sides by 2 to get sine isolated. And then I'm going to square both sides of this to get sine squared of t over 2 equals x squared over 4. Next, let me work on cosine. I can get that alone by dividing by 3, so I have y over 3 there. And then squaring both sides, we have cosine squared equals y squared over 9. Now I have the Pythagorean identity sine squared plus cosine squared equals 1. If I replace sine squared with x squared over 4 and cosine squared with y squared over 9, I have this equation now. And taking a look at that, so this is the rectangular form of the equation they were talking about and expressed in terms of x and y. So taking a look at what shape this might be, I noticed that we have two squared variables, so it's not a parabola. We have a plus between them, so it's not a hyperbola. And the denominators are different, so this is going to end up being an ellipse rather than a circle. So this then is an ellipse. That all matches up with what I have in answer choice A, or answer A. So I move on to the next one. I'm not going to keep letter A. For letter B, we've got two trig functions. So just like the first problem, I'm going to isolate them and square them to get them into an identity. So let me start by dividing by 4 to get the cosine by itself. Squaring both sides, we have cosine squared equals x squared over 16. And over here, let me divide by 4 to get sine by itself, and then square both sides to get sine squared equals y squared over 16. We again have the identity sine squared plus cosine squared, or cosine squared plus sine squared. I guess it doesn't really matter. And I can replace this with x squared over 16 plus y squared over 16 equals 1. Since I have two squared variables, it's not a parabola. Positive in here means it's not a hyperbola. And we have the same denominator, so that means it's going to be a circle. So we have x squared 16, y squared 16, circle. That all matches B, so on to the next. Here we go with letter C. Still haven't found anything that was wrong yet. So we've got two trig functions. Again, let me isolate the trig functions and then square them. So for my first equation, I can subtract 2 and then divide by 4. So I'll have x minus 2, all of that divided by 4. Now let me square both sides. That gives me a cosine squared, an x minus 2 quantity squared, which I'm not going to bother expanding, and a 16. Over here, let me add 1 and divide by 3, so y plus 1 over 3 over there. And then square both sides. I have sine squared equals y plus 1 squared over 9. And now let me use cosine squared plus sine squared equals 1 to plug these in. So I'm going to write, instead of cosine squared, I'll have this first expression, x minus 2 squared over 16. Instead of sine squared, I'll have this other expression, y plus 1 squared over 9. And since I have, again, squared variables, both of them, it's not a parabola. Plus means it's not a hyperbola. Different denominators means it's an ellipse, not a circle. So all that's an ellipse. And then it looks like I have the correct, well, no, this is a little bit different actually. No, I have to look down here. Yeah, it's C, looking at C. The first term is the same. After that, though, we have a minus instead of a plus. The actual fraction is the same, but they said it was a hyperbola, not an ellipse. So that's all wrong. I'm going to use C then at the end of this when I unscramble things and figure out what my mystery word is. For this next parametric equation, things are a little bit different. No more trig functions in here, so my strategy is going to be a little different. At this point, I'm going to isolate t in one of these equations and substitute for the t in the other equation. So basic kind of substitution setup. Between the two equations, I think this second equation is going to be a little easier to get t by itself in. A lot easier, really. I can just subtract 3 there to get y minus 3 equaling t. So now I'm going to replace t with y minus 3 in this first equation with the x. So I'll rewrite this as x equals negative, and now I'm going to have y minus 3 quantity squared over 2 minus quantity y minus 3 plus the 7 over 2 that's already there. I'm going to try to clean this up a little bit and maybe combine it into one big fraction if I can. So let's see, this first thing, I can distribute the negative, but before I do that actually, I need to expand this binomial. So we're going to have y squared, and then multiplying this together and doubling it for the middle term, I get a negative 6y. And then negative 3 squared is going to be a positive 9. For this next term, if I'm going to move this into one fraction, I need the same denominator. So I'm just going to multiply this second term by 2 over 2 in order to get a denominator of 2. And I'll worry about distributing that in a minute. And then the 7 over 2 already has the same denominator, so I'm just going to leave that as is. Let me distribute now. So this negative 1 gets distributed to this whole numerator. That gives me a negative y squared plus 6y minus 9. Moving on to the next one, distributing negative 2 to the y minus 3. That's going to be a negative 2y plus 6. And then I have this plus 7 coming along for the ride as well. So I have a negative y squared that I can't really do anything else with. 6y minus 2y is 4y, and then negative 9 plus 6 is negative 3. Negative 3 plus 7 is 4. So that is as good as it gets. This is x equals something with a y squared, so this is definitely a parabola sort of form if we only have one squared variable. And if I want to simplify this a little bit, I could call this negative 1/2 y squared plus 2y plus 2, and now I actually have this in kind of standard parabola form. It is a parabola, but again, taking a look at answer choice E, it says it's a circle, and this looks completely different. So definitely not going to match up there. So I'm going to keep E then and use that at the very end to rearrange things. For this problem, we're back to the trig functions, so back to our old strategy of isolating and squaring them. First one, we can divide by 2, so x over 2 equals the sign, and then squaring both sides, we have sine squared equals x squared over 4. For the next one, let's divide by 5, and then square both sides, so we have cosine squared equals y squared over 25. Again, using sine squared plus cosine squared equals 1, we have x squared over 4 plus y squared over 25 equals 1. We've got two squared variables, so not a parabola. Positive means it's going to be a circle or an ellipse, and different denominators narrows it down to ellipse. Looking at our answer, we have the same equation. We also have the same shape, so that works out, and we move it on. Next up, for problem L, we've got more trig functions and different ones, though. No longer sine and cosine. Now we've got tan and secant, so let's see how this works out. So let me isolate tan by subtracting 1 and then dividing by 3. So we can say tan equals x minus 1 over 3. And then if I square both sides of that, I've got x minus 1 squared over 9. And then tan squared. Now let me do the secant one. Subtracting 1 and dividing by 2, we have y minus 1 over 2 equaling secant. Squaring both sides, I have secant squared equals y minus 1 quantity squared over 4. And now for identities, I can't use sine squared and cosine squared anymore. Let me do one that has tan and secant squared. So the original identity was tan squared plus 1 equals secant squared. I can get them on the same side of the equation if I subtract secant squared and move the 1 over to the other side. So I can write, or actually even better, let me keep the 1 where it is and subtract tan squared to be with secant squared. So I'll write that as secant squared minus tan squared equals 1. If I rearrange the identity this way, I can keep this as a positive 1, which I like because that's kind of the standard form for all of these different conic sections. So, replacing things now, this first squared term can get replaced by y minus 1 squared over 4. This second one is getting replaced by x minus 1 squared over 9. So we end up with this as a final rectangular form. In terms of shapes, because I have two squared variables and we have subtraction between them, that's going to be a hyperbola. Taking a look at L, we have, let's see, the same equation. It's a hyperbola, so we're good to go on to the next one. For this next one, we got some more tan and secant going on. Let me isolate and square those. So we've got x plus 1 over 4 if I isolate the tan there. And then squaring both sides, we have tan squared equals x plus 1 squared over 16. Next up, for this one, we've got 1 being subtracted, then divide by 3. So y minus 1 over 3 equals secant. Squaring both sides, that's secant squared equals y minus 1 squared over 9. And just like the last problem, I'm going to use secant squared minus tan squared equals 1, one of my alterations of a Pythagorean identity. So that's y minus 1 squared over 9 minus x plus 1 squared over 16 if I substitute those in there. Same deal as before, two squared variables, subtraction. This is a hyperbola. Looking at n, it looks like I've got the same equation, almost the same equation. We have a plus in the answer instead of a minus, and they said it was an ellipse, not a hyperbola. That's different, so that means I'm going to keep the n. Here we go with problem O. On this one we have some more trig functions, so let's isolate and square those. For this first one, I'm going to add 1 and divide by 2, so I can write cosine of t equals x plus 1 all over 2. And then if I square both sides, I've got cosine squared and x plus 1 squared over 4. Now for the other equation, I'm going to subtract 2 and then divide by 3. So I've got sine of t equals y minus 2 over 3. Squaring both sides, I have sine squared equals y minus 2 squared over 9. And I've got cosine and sine squared, so let me use my cosine squared plus sine squared equals 1 identity, and then replace those. I guess these could be t's in here. I guess it doesn't really matter. There we go, as long as it's the same variable. So we can write x plus 2 squared over 4 plus y minus 2 squared over 9 equals 1. Since I have the same sign on these and both of the variables are squared and the denominators are different, this is going to be an ellipse. All of that tells me it's an ellipse, not a circle. Checking my answer, it looks like they identified it as a circle and the denominator is a little different on that first fraction there. So that means O is one of the letters we should keep, so I will record that. On this next one, we have tan and secant. Let's isolate and square those. So I have tan of t equals x over 2 if I isolate the tan. And then squaring both sides, I have tan squared equals x squared over 4. Next, I can divide by 4 to get secant alone. And if I square that, I've got secant squared equals y squared over 16. Now I can use the secant squared minus tan squared equals 1 identity that I've used on a few problems in this puzzle. So that's going to be y squared over 16 minus x squared over 4 equals 1. Since I have squared variables and subtraction, that's going to be a hyperbola. And looking at my answer, I've got the same expression and hyperbola, so this one checks out. On to the next. For this one, let's isolate cosine and sine and square those. So we've got x over 2 equals cosine. And then I square both sides to get cosine squared equals x squared over 4. Over here I've got sine equals y over 2. So sine squared equals y squared over 4. I can use cosine squared plus sine squared equals 1. So then substituting, I have x squared over 4 plus y squared over 4 equals 1. We have both variables squared. We have the same sign, and that also means that because we have the same denominator in each of these, this is going to be a circle, not an ellipse. Looking at my answer, R. This is a bit different. They have subtraction instead of addition. They said it's a hyperbola instead of a circle, so that means we're going to be keeping R. For problem S, this one I have no trig functions, so that means this is probably going to be a parabola, but let me do it out here. At the very least, it means I have to isolate t in one of these equations and then substitute for t in the other equation. Between the two equations, it looks like x is going to be a lot easier to deal with in terms of getting t by itself, because this is linear versus a quadratic. So to get t by itself in this first equation, I'm going to subtract 2 from x and then divide by 3. So I can write t equals x minus 2 over 3. And now I'm going to replace t in the y equation with x minus 2 over 3. So I'm going to write y equals 3 parentheses x minus 2 over 3, quantity squared, plus 6 times all that stuff. And then I have that 2 at the end along for the ride. I have some simplifying to do if I want to see if this is the equivalent of what they wrote here in answer S. But first, before I can really combine anything, let me expand this x minus 2 over 3. Let me actually square this whole fraction here. So we're going to have x squared minus, let's see, this will be 4x because I multiply these and double it. And then negative 2 squared is going to be 4. And the 3 squared gives me a 9 down there. Next up, I'm going to be a little bit tricksy about how I do this. I'm going to end up with fractions, so I want to make sure that at the end of this next step I have a common denominator. So what I can do on my first fraction is I can reduce this 3 and this 9 to give me a 3 in the denominator. And then I'll just leave the stuff that was already up there. So we have x squared minus 4x plus 4. That doesn't change. For this next fraction, I could reduce the 6 and the 3, but then I'm going to lose a 3 from my denominator, and I'm going to have to get it back to match this first denominator, which is annoying. So instead of using the 6 that way, I'm going to multiply the 6 by the numerator instead. You have to do one or the other, divide or multiply, so I choose multiply. So this is going to be a denominator of 3. We're going to have 6x minus 12. Next up, I have a plus 2. I want to get a denominator of 3 on that as well, so I can rewrite the 2. If I multiply by 3 over 3, I can rewrite this as 6/3. Now I have a common denominator of 3, and I can combine all these fractions together. So we'll have a 3 downstairs. This x squared is one of a kind, no other squared term, so that stays as is. We have a negative 4x and a 6x. Those can combine to give me a positive 2x. We have a 4. We have a minus 12. That's a negative 8 subtotal. Negative 8 plus 6 is going to give me negative 2. So that's the final combined version. Now this doesn't quite match what I have in choice S, so one more thing I could do is divide each of these things in the numerator by 3 to get it into more of a standard, less fraction-y form. So x squared over 3, I can write that as 1/3 x squared. This next one I can do 2/3 x, and then minus 2/3. This is clearly a parabola. We only have one squared variable. Checking answer S, it looks like everything that I wrote here is reflected in that answer. So this is actually correct, and I don't get any letters out of that. For letter T, let me isolate and square these trig functions. So we can actually go ahead and just square the x equation right away because secant's already isolated. So secant squared equals x squared. There you go. For this next one, I can divide by 4 to get tan by itself, and then squaring gives me tan squared equals y squared over 16. Let me use secant squared minus tan squared equals 1. So that's going to be x squared minus y squared over 16 equals 1. I have subtraction and squared terms, so that's going to be a hyperbola. Looking at my answer here, this looks a little bit different than what I have over here, and they said it was a parabola, so definitely not what I'm looking for. So I'm going to keep that letter T. For problem U, since I have trig functions, let's isolate and square those. Working on the first one, we can subtract 2 and divide by 3. So we have tan equals x minus 2 over 3. Squaring that gives me tan squared equals x minus 2 squared over 9. Now over to the other equation, I'm going to add 1 and divide by 3. So we have y plus 1 over 3. Squaring everything there, we have secant squared equals y plus 1 squared over 9. I'm going to use secant squared minus tan squared equals 1. So we have the x minus 2 squared over 9. Actually, no, we'll do the y plus 1 squared over 9 minus the x minus 2 squared over 9. It's secant squared minus tan squared. There we go. We have to make sure we get the order correct because we have subtraction, so I can't just write these in any order I feel like. Now, since I have subtraction and squared terms, that's a hyperbola. Looking at U, we've got y plus 1 squared over 9 minus x minus 2 squared over 9. That matches hyperbola. So U is correct, and we go on to the next problem. So here we go with the last problem they've given us. We're going to isolate these trig functions and square them. So we have x minus 2 over 3 equaling sine. Squaring all that, we have sine squared equals x minus 2 squared over 9. For this next one, I'm going to subtract 2 and divide by 3 to get cosine alone. So cosine equals y minus 2, all divided by 3. Then squaring that, we have cosine squared equals y minus 2 squared over 9. I can use sine squared plus cosine squared equals 1 here. So that's x minus 2 squared over 9 plus y minus 2 squared over 9 equals 1. I've got squared terms. I've got positive here, both of these positive. So it's a circle or an ellipse, and the same denominator means it's going to be a circle. So V, they identified this as an ellipse, and one of the denominators was also different. So I'm going to keep letter V. So we've identified all the letters of problems that were incorrect in the answers. Now we have to unscramble these to form something that has some implications for this whole parametric conic section thing. So let's see here. I've got a V, not many words with a V in it. We also have a C, we have an OR, we've got a bunch of things. So let me think here. Well, this whole puzzle was about converting between different forms. So I wonder if that's it. It's got enough letters. We have a C, we have an O, an N, we do have a V, an E, and an R, and a T. Yep, convert. There it is. Till next time, Mr. Sutton signing off.